Okay, so for today, we're going to cover Hess's law, all right? And really, for the most part, it's kind of one of my funner things to do when it comes to some of this stuff, because it's kind of like puzzle pieces, like the reactions are little puzzle pieces. We're going to flip them around, manipulate them so they fit together in the right way and creating the reaction that we're looking to get to, okay? And the nice part is with heat and all that sort of stuff, you know, it's independent of the process in between. It ultimately is the amount of energy you start with and the amount of energy you finish with. Everything that happens in between, right? There could be 3, 4-step, 5-step reactions, but ultimately, in the end, it's just a difference between where you get to. So, not the specific pathway and stuff. So it's really kind of neat. But Hess's law allows us to take small reactions and add them together to determine the enthalpy for a reaction. So far we've done like the standard law where we looked at heats of formation, added them together, did products minus reactants and stuff. We've done the heat of formation where we measured the heat given off in a lab and we figured out, okay, we burned up this many moles of the substance, it created this much heat, we can determine kilojoules per mole there for delta H, right? And here's just another way to do that, and Hess's law is the way we're going to do that, okay? So we have, every example is going to have an overall reaction right here. So they want us to calculate the delta H of the reaction right here. For this reaction here is what we're trying to get to, right? That's our overall reaction that we want, okay? And these are the two reactions that we can use to add up to get to that overall reaction, okay? So we're going to add them together, and hopefully when we add them together, we get to this. Now, this first one is really nice and easy, okay? So if we look at these reactions, so maybe I'll put over here. So the sum of the enthalpy of the individual steps gives us the overall delta H for the reaction. So we're going to add up these separate parts, these separate puzzle pieces, and we might have to manipulate the puzzle pieces as we go in order to add them together to get to that overall reaction we're trying to get to, okay? So when we look at a couple pointers that we want to do here is we want to look at location of products and reactants. And line up the individual reactions accordingly. Okay, so that's one of those things that's going to help us out. So if we look at this overall reaction, we have our reactants, we've got our products, so we want to look for those pieces in the parts, right, in our individual steps here, right? So if I look for N2 down on the reactions below, I only see N2 present in the first reaction there, right? And it happens to be on the reactant side. Okay, great, that's a good sign. So that's probably a sign that I want to keep that reaction kind of written the way it is. I don't need to flip it around, okay? I don't need to multiply it by any numbers or anything yet. You know, we want to just leave it written the way it is, okay? Is O2 there too? Yeah, it is, and it's actually in this other reaction too, so that's kind of interesting, all right? And then with this next one here, NO2, all right? Do you see NO2 anywhere except for the product side right here? We don't, so that's a sign that, okay, we want to keep that reaction written the way it is as well, okay? So what we're going to do is we're going to leave those reactions kind of written the way they are and just add them together, all right? So we're just going to add these guys together, all right? And we're just going to add everything together. Now, things that are on both sides, if they're on the reactant side and the product side, we can cancel them out. All right, they're intermediate, so we're just going to cancel them out. So see how we have 2 NO on the reactant side here, and we've got 2 NO on the product side? They cancel each other out. Okay, so we can cross both of those out. We have the same number, so we're going to get rid of that guy entirely. So there's no other ones that cancel out. So we're just going to add what's together on the reactant side. So over here, we've got N2. Right? And how many O2s we got? 2. plus 2O2 going to 2NO2. Okay? Now, with the delta H's, all we do is add them together as well. Yep.
So why wouldn't the twos cancel out?
They're on the same side. They're both reactants. So they stay together. If they're on opposite sides, they would cancel. Mm-hmm. Yeah, so we have the reactants together. We have the products together. So that's what we're left with. And what you're hoping for is that, hey, that matches our overall reaction. And it does. So that's nice. So we're good. And we want to look at, and then all we do is add our delta H's together. Okay? So 180, right, plus a negative 112, right? That's going to be, what's that, 68? Okay? So delta H, and I'll just kind of write it out as 180 plus the negative 112, right? So it equals a positive 68 kilojoules. Okay? And that's it. Then we're done. Okay? That's it. That easy. All right. Now they're going to get harder. Okay? So it's pretty easy. All right? So, because we're going to manipulate we're going to move these puzzle pieces around so they fit together. Okay? So the next one here, failure number 2. All right, we got a reaction here. We got graphite going to diamond. All right, we want to see what delta H value is for that. All right, so we've got our 2 puzzle pieces here, graphite plus O2 making carbon dioxide, and then diamond plus oxygen making carbon dioxide as well. And then we got our heat associated with those guys. So we look at these guys. Graphite is on the reactant side. In this first reaction, it's written like that. So that works, okay? Diamond is on the product side though, right? The only place we have diamond is in this reaction here, and it's on the reactant side. So what we need to do is we're going to flip this one over. Okay, we're going to flip that. So I'm going to rewrite it as CO2 going to O2 plus C diamond. Okay, and the delta H value, because we flip it around, changes sign. Okay, so you just flip the sign. So if you flip a reaction, you change the sign of delta H. So if you flip a reaction, change the sign of delta H. Okay, for that reaction. All right, so we flipped that one, so I'm going to cross it out now just to kind of clean stuff up a little bit. All right, and just maybe okay, so now what we want to do is we want to add those 2 reactions together. Sometimes it might be helpful to, I'm just going to rewrite this other one right down below and just leave it the same just to write it there next to it. Okay, just to write it there next to it, just so I have it then right there, just to make it a little cleaner, because sometimes it just makes it's a little difficult. Sometimes if you're manipulating a lot of them, you might just want to rewrite that one. Okay, so then if we look at these and we add them together, we want to add these guys together now, right? O2s cancel out, right? Because they're on opposite sides. Right? O2 cancels, the CO2s cancel, right? And you're left with graphite going to diamond. And our delta H is equal to a positive 2 kilojoules. Okay. All right, so there you go. Okay. All right, so let's do the next one here. So you saw one there where we flip a reaction, we change the sign to delta H. All right, last one here. Well, this last one on this page here. So let's take a look at this one here. So this is the overall reaction we're looking for. And we've got these three reactions to play with now. Okay? So if we look at the first reaction, right? Okay, there's some stuff here. There's H2 and C. They aren't even in the overall reaction, right? So we're going to have to get rid of those guys somehow. But there's C2H6 in there, right? So we definitely want to flip that one around, don't we? Okay? So we're definitely going to flip that one around. So we're just going to rewrite that one. So we're going to flip it. All right? And if I look at the other ones, there's carbon dioxide, there's water, okay, oxygen and stuff. These ones look good, right, because the carbon dioxide and water are on the right side of the reaction, okay? So those ones look pretty good, but what are we noticing about what's going on with those, though? What's that?
They don't have water?
Well, no, there's water here in that reaction, right? But what's different about them in the overall reaction? Yeah, there's more than just one, right? We have just one here, but we have 4 up there, right? And we only have 1 here, but there's 6 up there. So, and then also, as I'm looking at this too, what do we notice about C2H6? There's 2 of them up here, but there's only 1 there, right? So what we're going to do is we're going to multiply each one of those reactions by the amount we need up there, and hopefully, when we add it all together, it looks pretty good. Okay, so we're going to multiply this one by 2. We're not only going to flip it, but we're going to multiply that one by 2. We're going to multiply this one by 4, and we're going to multiply this one by 6, right? Okay, so what we're going to do is we're going to flip it and then multiply it, and so I'm going to rewrite all these as we go. All right, so the first reaction, we want to flip it around, and we want to multiply it by 2. So we have 2C2H6 going to 4 carbon, and that's 6H2. And now the delta H is going to be, yeah, so whatever you do to the reaction, you do to delta H. Okay, so our new delta H value is positive 84, but then we multiply it by 2. So that's 169.4, right? Negative, or I'm sorry, positive. Is that correct? Okay. All right, so we got that one. So I'm going to put a line through it because we're done with it. All right, the next one we just want to multiply by 4. Right, so we got 4 carbon plus 4 O2, and that's kind of nice. I'm already starting to notice like 4 carbons are going to cancel, right? So that's good. We want to get rid of those. And we get 4 carbon dioxide. So our delta H value, or new delta H value here is, I'm going to need some help now. I can't do that one. Negative 1,574. Okay. The next one, okay, I'm going to cross that one out because we're done with it. Next one, is we want to multiply by 6. So we got 6H2 plus 6 times 0.5 is 3O2 going to 6H2O. So we multiply that delta H by 4, or I'm sorry, by 6. Negative 1,452. Great. All right, now we got to add them all together. Pull up the red pen and start crossing stuff out, right? So I have 4 carbons on the reactant side. I got 4 on the products. So those are gone. I've got 6H2, 6H2s. Okay. Oops, those guys are gone. Okay. And it doesn't look like anything else cancels out. So we end up with 2 C2H6 plus is a total of 7 oxygens, 4 carbon dioxide, and 6 H2O. And what do we get for the total delta H? 856.6. That's kilojoules. There we go. Great. Yes, sir.
Delta H is ever cancel out.
What do you mean?
Like if they were to be the same, like.
Well, if one's positive, one's negative, then they would add up to 0. You just add them up. You're just always adding them together. Okay. Yep.
What would our answer be? Is it the delta H or is it the delta H?
It's the whole thing. Yeah, it's the whole thing. Yeah. Yeah, so there you go. Yep.
So how did you figure out, like, oh, that B needs to be multiplied by 4 and C needs to be multiplied by 4?
I'm going off of this is like the box, you know, like when you're putting together a puzzle, right? And you're looking at the picture on the front of the box, and you're trying to put all the pieces together to make that happen. That's what this is telling. That's what this is right here. That overall reaction, that's what we're looking to get to. So when I look down here, I'm like, well, we only have 1 carbon dioxide, but I need 4. So I multiply that one by 4. Okay. Any other questions? All right, so you saw the different scenarios, and you'll kind of see, you just got to take some practice. Takes a little getting used to. They get a little bit more difficult. Okay, but there you go. Okay, I'll let you guys go and just do some practice with this. And that's that.